the next presenter, that would be Stefano Savio, back to Italy again. Well, thank you, the Italian guys. Thanks for supporting us and accepting to present in this event.
Good afternoon to everybody. I'm Stefano Savio, a student from Polytechnic of Turin. And today I'm going to present you what I've done for my bachelor degree in mechanics last year. I've designed a magnetic gear using EMS and SolidWorks. And thanks to EMWorks, I had the possibility to generate a lot of simulations and interesting results about it. I'm going to start with a brief introduction about what it is, a magnetic gear. I think that many of you know exactly what it is, but I will introduce you about the most important things. Then I will analyze the parameters that we need to take care of when we design a magnetic gear. And in the end, we're going to see how to design and modeling it using SolidWorks and EMWorks. And then we're going to see the final results of my work. First of all, what is a magnetic gear? Using simple words, it works exactly like a mechanical gear. The main difference is just that all the components that constitute it doesn't interface with each other by contact, but just with electromagnetic fields. So this is an interesting point, because it lets us to reduce a lot the losses. The components will have a longer life, for example, and of course we will have in general a higher efficiency compared with the mechanical gear. Another interesting point of this of the magnetic gear compared to mechanical gear is that they need low maintenance. For example, they don't need oil, or there are not parts that contact with each other. So it can be used, for example, in situations that you may have a lot of difficulty putting hands on and to eliminate some problems or fixing something. Instead of these interesting features, we need to know that they have, of course, a higher cost compared to mechanical gear, because we have the main things that characterize a magnetic gear are the permanent magnets, which are extremely costly. So we need to take care of this thing, of course. And in the end, it presents a structure more complex with respect to a mechanical gear, because it's true that the components doesn't touch each other, but we need to take them extremely closely, because we need to interface to let the different electromagnetic fields to interact with each other. So they need to be extremely closer, but don't touch between them. So it's a little bit difficult in the end to create this structure without any problem. So a magnetic gear is made of 3 different parts. An outer rotor, which we can also call it like a low-speed rotor, consisting of the external metal housing and pairs of magnets. In my case study, I've used 15 pairs of magnets. And the second important part is, of course, the inner rotor, or the high-speed rotor, consisting of an internal metal housing, different from the low-speed rotor, and 2 pairs of magnets. Between the outer rotor and the inner rotor, there is the metal gearbox. The metal gearbox is, of course, made of metal, its name, and is made of N-pole pieces. This part of the magnetic gear is extremely important, because it interconnect the different electromagnetic field generated by the inner rotor and the outer rotor to mesh between them and connect let the outer rotor to generate torque. So So it's an extremely important part of the magnetic gear. Okay, talking about the parameters analysis, we need to take care of different things. First of all, the metal gearbox radius. As I told you, it's an important part of our gearbox, and as we can see in the graphs, increasing the metal gearbox radius and also the thickness of the magnets, for example, the torque increases a lot. There's just one point that we need to take care of, is that the thickness of magnets, of course, more magnets or magnets bigger is of course useful and better for torque transmission, but it increases, of course, the costs, and we can't always have that disponibility to create exactly what we want. So we need to make a decision between dimension of magnets and metal gearbox in order to achieve a good torque with reasonable cost. Another thing extremely important to take care of that we're gonna see in practice later is the dimension of the air gap between components, because as we can see in the graph on the right, low part of the slide on the right, an increase and a minimum increase of the air gap define a great loss of torque. So it's extremely important to define it correctly and create a structure of our magnetic gear that is able to maintain the air gap constant. And in the end, an important factor that we need to control when we design our magnetic gear is the cogging factor. This factor, as you can see in the formula, is depending on the pole pairs of the gearbox and on the number of magnets. So if this factor is minor or equal to 1, everything is working. It's probably working correctly in theory almost. But if this factor is bigger than 1, probably we will have a lot of oscillations in the transmitting the torque between the inner and outer rotor, and this can create a lot of problems, especially structural problems. Then we can start the design and the modeling using our software. So first of all, we need to choose a goal. In my project, I choose to obtain a gear ratio of 7.5. We call it gear ratio as we do in the mechanical gearbox, just because the principle is the same. We can make a demonstration. I don't have it with me, but it exists. That the Lewis formulas can be applied also to electromagnetic gearbox. So it's not a problem to define it as a gear ratio. So after we have defined the gear ratio, the number of magnets of the inner and the outer rotor, and the number of pole pairs on the mechanical gearbox, we can control the cogging factor, and then we can start our simulation on EMWorks and SolidWorks. In order to do that, we defined 3 different components on SolidWorks, which are the high-speed rotor, the low-speed rotor, and the modulator, which is the mechanical gearbox. In the end, after some work on it, I discovered that EMWorks wasn't able to analyze correctly my model. So using the service that you provide to me, I discovered that I need to create also an airbox, because EMWorks didn't recognize that what was present between the different components. So we need to define another blocks, that is this one in gray, that in fact let us define it as air. So it was an important point. After that, we can start using the EMWorks suite a new study. Of course, we need to select the analysis type magnetostatics and also check out the parameterization point, because our study will be possible with I don't know how to say. We parameterize one thing, that is the angle of the inner rotor, in order to generate or simulate the movement on the inner rotor. So we can see how the different fields, the magnetic fields of the inner rotor and the one on the outer rotor, interact between each other. So after we made the parameterization, we can define the different materials of the components. EMWorks has a great library of materials, so I didn't need to add the different materials. There was everything ready to be used. And after defining the materials, we also needed to define the direction of the magnets, of course, because if we didn't define it correctly, probably our model will never work. So with the coercitivity direction, we set it to cylindrical, and everything works fine. After that, we started the parameterization, and as I told you, we choose the angle of the inner rotor in order to see the different position of the rotor, how the field will interact. And then, last but not the least, we defined the force torques, or the virtual work. This is the most important thing of our simulation, because it creates something that is clear to us when we create a simulation, if our model is working correctly. So with this, we can also create some real simulations, some videos that I will show you later. During the modeling, of course, there are three important things that we need to care about. First of all, the correct definition of the materials. I spent a lot of time because I defined wrong the material of the magnets, and I was obtaining these results. As you can see, is not interesting, because there is not a magnetic field working. That is any magnetic field working on it. So after some trials and errors, I fixed it, putting the correct materials on magnets and the inner and outer rotor, and I obtain something more interesting. Then another important point is, of course, to choose the correct meshing solution for your simulation, because EMWorks provide a lot of meshing solutions, some more simple, some more complex, and of course you need to choose it different from your model. And of course, another important thing is the correct orientation of the virtual work. If you put it wrong, you're gonna see nothing on your screen. Now, these one are some videos, if I'm able to. Okay. In the end, you can see your simulation working, and I think that this is the most interesting part, because as we can see, there is a specific angle for which the magnetic field interaction between the inner and the outer rotor is maximum, and is when you can see the red point on the mechanical gearbox. This is another simulation. Okay. You can also show the simulation with a vectorial aspect, and this could be useful. Maybe not this one, because there are a lot of vectors, but just to let you know, it could be useful because there you can see exactly where are going the electromagnetic fields in your simulation. In the end, we obtained some final results. This is the first significant result that I obtained, fixing the external rotor. During this first result, I fixed an air gap of 4 millimeters, and the torque transmitted was about 24 nanometer Newton meter. And as first result, I was not very happy about it because from my simulations, from a theoretical point of view, it was extremely low, this torque. So knowing that the air gap is extremely important, I reduced it of to 2 millimeters, and I obtained a torque transmit of 36 Newton meter, which is extremely better than before. In the end, on the we can see what's happening on the internal rotor and on the outer rotor. Of course, always in the EMWorks. And as we can observe, on the internal rotor, there are a lot of oscillations, which are the green and the red one lines. Then in the external rotor, we have practically negligible oscillation effect and a great torque transmit. In order to see if we have done a correct dimensioning of our model, we can compare the results with the theoretical formula. And as you can see, as the internal rotor produced a 43 Newton meter torque, the external torque see a 325 Newton meter torque. We obtained that our choices of air gap, our choices of pole pairs, pole pieces is correct. In fact, the gear ratio is very similar to the theoretical one. We have chosen 7.5 gear ratio, and we obtained a 7.5 result. So I think that is an interesting result and a successful result.